Okay, good morning, everyone. So sorry a little bit late. There is connection gets slow to the Zoom just now, but we will continue today with the superposition, the discussion on superposition, which we have started yesterday. So we are going to continue further. Okay, so in homogeneity, basically, yeah, last session yesterday we discussed that in homogeneity to get the answer we assume that the answer we assume the answer to have a certain value, yeah. Afterwards we go backward, solving the problem backward, solving the problem backward, and then when we get to the source of the, for example, the value of the voltage source, then the problem itself gave another value, then we have the multiplication constant multiplication factor. So by using that multiplication factor, then we can implement it to multiply to the previously assumed value. Okay, let's try some example here. Yesterday we have got the principle here, but maybe it's a bit difficult to understand it without proper examples, without examining proper examples. So here, yeah, we first assume a certain output value, for example, V dash output here, 1 volt. And afterwards, we compute the resulting source value, the V dash S here. From there, we use the linearity principle. With if V dash S will result in V output, V dash output, then multiplying with a certain K V dash S will be equal to, will result in K multiplied to V output dash. Okay, so this K times the V dash S is the original, the Vs according to the problem. Okay, let's give some example here. So for example, the circuit is given, you're having two mesh and then 12 voltage independent voltage source at the left. And the question is calculate V output. Okay, calculate V output at this 2 kilo ohm resistor. So first, let's assume that V output here, which is equal to V output equals to V2 here, we assume to have a value of 1 volt. Okay, then by assuming this value of 1 volt, then we know that I2 can be calculated. V2 divided by the resistor value, 1 volt divided by 2K, and we obtain 0.5 milliampere, the value of I2. So from here, then we can calculate V1. V1 equals to I2 multiplied by 4K ohm here plus V2. 4 kilo ohm multiplied by 0.5 milliampere is 2 volt plus 1 volt equals to 3 volt. Obtaining V1, we can calculate I1, the current flowing through the 3 kilo ohm resistor. Okay, 3 volt divided by 3 kilo ohm. So we obtain I1 equals to 1 milliampere. Yeah. So I1 here is now obtained and I2 is obtained previously 0.5 milliampere. Then we can calculate IO here, which is from using Kirchhoff current law. Yeah, so IO will be equals to I1 plus I2. So 1 milliampere plus 0.5 milliampere equals to 1.5 milliampere IO. From here, then we can calculate V output. So V output will VO here, not V output, sorry, V0. V0 here will be equals to I0 times 2 kilo ohm plus V1. Okay, V0 equals to 2 kilo ohm times 1.5 milliampere is 3 volt plus V1. V1 is 3 volt. So V0 is 6 volt. Okay. However, the original value of V0 here, according to problem, is actually 12 volt. Okay, so 12 volt is a 2 times multiplication factor compared to the assumed V0 here, 6 volt. So we know then that the correct V output here should be 2 times also of this assumed V output here, which is 2 times 1 2-fold. Okay, so here using homogeneity principle of superposition, if V output 6-fold, we will get V0 6-fold, or the independent source here 6-fold. Then we will get 1-fold of V output. It means if the V0 is 12-fold, then we will obtain V output equals to 2-fold. Okay, so this is the principle of homogeneity. Let's give another example. Here we have a current source, independent current source here, I. Okay, and the I is 6 milliampere. Now calculate I0 using homogeneity. Okay, of course we can use Kirchhoff current law and current divider to calculate E0, but now E output. Yeah, but now try to calculate using homogeneity principle. So assuming that E output here is 1 milliampere here flowing through this 3 kilo ohm, so then it means we can obtain VO here. Okay, VO here, V1 yeah, here, which is 3 kilo ohm times 1 milliampere, or 3 volt. Okay, then we can calculate current flowing through the 6 kilo ohm resistor. 3 volt divided by 6 kilo ohm equals to 0.5 milliampere. It means the current flowing through the 2 kilo ohm resistor can be calculated using Kirchhoff current law. 0.5 milliampere plus 1 milliampere equals to 1.5 milliampere. Then from here, we can obtain Vs, yeah, because this is 1 milliampere. Vs here, the voltage at this point will be equal to this current multiplied by this resistor plus the voltage at this point, at this node. Yeah, 1.5 milliampere times 2 kilo ohm equals to 3 volt plus 3 volt. Yeah, so equals to 6 volt. So 6 volt is the voltage here. From here, then we can calculate the current flowing through this series resistors, 4 kilo ohm and 8 kilo ohm. Yeah, 6 volt divided by 12 equals to half milliampere. Half milliampere, this is 1.5 milliampere. So then we know the value of the current independent current source is 1.5 plus 0.5 equals to 2 milliampere. However, here the problem states that the independent current source has a value of 6 milliampere, right? Which is 3 times multiplication factor from this 2 milliampere. So we know then that actually this I output is not 1 milliampere, but instead how many? Here, if this is triple, this 2 milliampere, it means here equals to, anyone?
3 milliampere.
3 milliampere. Okay, yeah. So this is the homogeneity principle. So in homogeneity principle, first we assume a value to the parameter which is being asked. In this case, it is I output here. From there, we calculate backward towards the current source. Okay, and then the actual current source stated by the problem is 6 milliampere. So then how many times it is from the obtained backward calculated result from the previous assumption. From there, then we multiplied that assumption current, that assumed current, with that multiplication factor to obtain the correct the correct parameter. Yeah. So this is homogeneity principle. Okay. So now we go to what we call a source superposition. Source superposition is a direct application of linearity. Yeah, in the previous chapter, maybe we have learned how to, when voltage source is in series, then we learn how to add the voltage sources value into a single voltage source. Or when we have parallel current sources, we can add the value to make them into a single current source. So in source superposition, basically, we calculate the effect of each of the source to the output parameter. Yeah. After that, then the overall output, the overall result of the output parameter can be calculated from the sum of this the output parameter based on the effect of each of the source. It is normally used when the circuit has only a few sources. So for example, here we have two sources, one voltage source and one independent current source, and we have a load resistor here and current flowing through that load resistor. So due to the linearity, the voltage at this load will be equals to A1 times Vs plus A2 times Is. Yeah, so A1 Vs is the voltage at this resistor contributed by the independent voltage source Vs. Then A2 Is or VL2 here is the voltage at this load resistor contributed by the independent current source Is. Okay. So then V1L can be computed by setting the current source to 0. So the current source, how to set the current source to be 0? We make it as open circuit. Yeah, with the current source, we make it as open circuit, so no current flowing through it. And then solving the circuit, obtaining the VL1, the contribution at the contribution of the voltage source to the loading the loading voltage here. Then after that we calculate VL2 or V2L, the contribution due to the current source by making the voltage source 0. How to make voltage source 0? By short circuiting the voltage source. Okay, let's try now. This is so here the current load, the current at the load as well as the voltage at the load equals to first the contribution due to the independent voltage source Vs here by making the current source here 0, which is by opening the by making it open circuit, yeah, so that it has a 0 value of current source. Basically, open circuit current source equals to a current source which has a 0 value, plus the contribution of the contribution of the voltage load and current load due to the current source by making the voltage source 0, which is done by short circuiting it here. So when the short circuit, we know that the potential will be 0, right? They will be equal potential, equal voltage. So due to the linearity of the models, we should have IL equals to IL1 plus IL2, and VL equals the voltage at the loading here, at the load resistor here equals to VL1 plus VL2. So this is the principle of superposition. Yeah. So the approach will be useful if solving the two circuits is simpler or more convenient than solving a circuit with two sources. Yeah. So if it is done independently will be easier, then this method will be useful. Yeah. We can have any combination of sources. Then we can partition any way we find it to be convenient. For example, we want to compute I1. I1 is, where is it? I1 is, I think, this one. Yeah. Of course, we can use loop method. We can also use Kirchhoff current law, nodal analysis. But now we use superposition. First, we calculate I1 due to the contribution of V1T, the first independent voltage source only. So in this case, the second independent voltage source is made 0 by short circuiting it. So this one short circuited. Then, secondly, after we obtain the value of I1 dash T here, we calculate the I1 dash double dash T, yeah, which is calculated by making the first independent voltage source to be 0 by short circuiting it here at this line. Okay, so the effect due to the second independent voltage source only. So once we know the partial circuits, we need to be able to solve them in an efficient manner. So for example, here, when this is short circuited, so the equivalent resistor of this is 3 kilo ohm parallel with 6 kilo ohm, then in series with this 3 kilo ohm. Okay, so from here we obtain then I1 dash T equals to V1T divided by 3K plus this 3K parallel with 6K, yeah, 3K, 6K divided by 3K plus 6K. Okay, so this is 9K. So this is how many? 18K. Yeah, 18K. So then we obtain 3 plus 6 is 3 times 6 is 18, yeah, divided by 9K. 18K square divided by 9K, which is 2K. 2K plus 3K equals to 5K. So the I1 dash T, so the contribution due to the first independent voltage source is this. Yeah, this is the current. Yeah. Then we calculate this by short circuiting the first independent voltage source. We have only the second independent voltage source. So this is also can be made into an equivalent resistors, okay, which is 6K plus 3K in parallel with 3K, or 6 plus 1.5, right? 7.5K. So here then, yeah, so here we obtain the value. So I double dash T, the voltage here is minus, where is it? 2T, and then here 3K 3K times 3K, so this is supposed to be how many? 6K, yeah, 7.5, yeah, supposed to be. And we obtain this value, okay? Yeah. Wait, so, okay, this is the I2 dash, this is the current flowing through here. It means the current flowing through this 3 kilo ohm, this is a current divider, right? So this can be calculated from here. This is the current for the current flowing through this, and then multiplied by the 3K divided by 3K plus 3K. This is the current divider formula, remember? So this is the contribution due to V2T to the I1. So from here, then we obtain, this is also actually can be calculated using loop equation. The total current or the current I1 will be equals to this plus this value, okay? So this is the principle of superposition. Let's give some example. Compute the V output here, yeah, at the voltage across this 6 kilo ohm resistor. Yeah, if we have this this circuit having one independent current source 2 milliampere and one independent voltage source 3 volt. So first we calculate the contribution by the independent current source. So we set this independent voltage source to be 0 by short circuiting it like this. So from here, then we obtain, so this is basically a current divider, right? So this 1K plus 2K is 3 kilo ohm. So the current flowing through this 6 kilo ohm is how many? 3 divided by 6 plus 3, yeah, times 2 milliampere. Or this is 1/3, yeah, 2/3 milliampere. Okay, so let's see if this is correct. Yeah. So this is current division, 1K plus 2K divided by, or 3K divided by 9, yeah? So 9K, or 1/3 of this 2 milliampere. Okay. Then the V output of at this will be this value, this current, times the 6 kilo ohm. Yeah, or why is it 4-fold? Yeah, the I output here is 3K divided by 9K, 1/3. So two-third milliampere times 6 kilo ohm. Yeah, right. 2/3 milliampere times 6 kilo ohm. Yeah, it is fourfold. Correct. So this is contribution due to the voltage, due to the current source. And after that, we calculate the contribution due to the voltage source by setting the independent current source to be 0 by making it open circuit like this. Okay, and this is basically a voltage divider. So voltage at 6 kilo ohm will be 6 kilo divided by 6 plus 3 kilo ohm times 3 volt. Yeah, so or 6 divided by 9, 2/3 times 3 is 2 volt. Then the value of V output will be V output dash plus V output double dash here. So 4 volt plus 2 volts equal to 6 volt. Okay. Yeah, of course, we can use also loop analysis or nodal analysis if you like, and we should have the same result here. However, this is actually seems to be more straightforward, right, compared to if we do nodal analysis or loop analysis. Another example here. So we have a circuit with one independent voltage source 6 volt and another independent current source 2 milliampere. Calculate the output voltage across the 6 kilo ohm resistor using superposition. First, set the current source to 0, yeah, to make it open circuit, so it becomes like this. So then we can calculate this using we can calculate first the equivalent resistor, okay, and then make it as a voltage divider. If V1 is known, then V output dash is obtained using a voltage divider formula, yeah, this one. Okay, V1 can be obtained by series parallel reduction and divider. So here, this is 2 kilo ohm here is in series with the 6 kilo ohm, yeah, becomes 8 kilo ohm. So then 4 kilo ohm is in parallel with that 8 kilo ohm, yeah, becomes then V1, yeah, so it is this value divided by this value plus this value, 2K plus this value multiplied to 6. So we obtain the value at the V output. We calculate again using voltage divider, from V1. 6K divided by 6K plus 2K times V1. Here we obtain 18/7 volt. Then we calculate V output due to the contribution by the current source by setting the voltage independent voltage source to be 0 by making it short circuited like this. Okay. So then we can use the formula current divider to calculate the current flowing through the 6 kilo ohm resistor here. Okay, so when in doubt, or you can always redraw it. So for example here, because there is something connected like this, basically it's become short circuited. It is basically a single node. So you can redraw it as something like this. So the 2 kilo ohm and 4 kilo ohm is in parallel, become a single resistor like this. This is in series with the 2 kilo ohm, and they are in parallel with the 6 kilo ohm. So from here, we can calculate I2 flowing through the 6 kilo ohm resistor using a current division formula like this, 2 kilo ohm plus 2K parallel 4K divided by 2K plus 6K plus 2K parallel 4K times 2 milliampere. Here we obtain the value I2. From there, we can calculate the output double dash. Okay? After that, then we can calculate the final V output from the contribution of the voltage source here, V output dash, and from the plus the contribution from the current source, yeah, the V output double dash. Okay. Okay, another example here, compute using source superposition. So we have 3 sources here, 2 independent current source, 4 milliampere, 3 milliampere, then 1 independent voltage source, 9 volt. We are asked to calculate the I output here flowing through the 3 kilo ohm resistor. First, consider only the voltage source. It means we open circuit the other 2 sources, the other 2 independent current source. Okay, if it is short circuited, then this is short circuited. This is short circuited also. Then this resistor is floating, right? This resistor is floating. A floating resistor like that can be neglected. So we only consider the current flowing through this single loop. Right? So that IO1 will be equals to 9 volt divided by 3K plus 3K. 9 volt divided by 6K, which is 1. We obtain negative 1.5 milliampere, but be careful of the direction, yeah, since the direction of the loop here is here, the I 1.5 milliampere is this direction. However, I01 is drawn like this. Means then the sign should be negative. Yeah, IO1 equals to negative 1.5 milliampere. Then we consider only the 3 milliampere source. So the 4 milliampere source is short circuited. The 9-volt source is this one is open circuited, and the 9-volt source is short circuited. Okay, so from there we obtain this circuit 3 milliampere, which is clearly this is a current divider, and then we can find the IO2 equals to negative 1.5 milliampere. Okay, because then after that, the third one, we consider the contribution from the 4 milliampere current source. This 3 milliampere is short circuited, and the 9-volt voltage source is short circuited. Okay. So from here, we obtain I03 to be 0 ampere. Yeah? Because why is that? Because here they are parallel, but no current flowing through here. Okay, because it is also a floating. This one is in parallel with this one. They are floating branch. A floating branch is not connected because they are short circuited. The current only flows through this resistor. Okay, so the current flowing through here is 0. It means the current, the IO due to the contribution of 4 milliampere source is also 0. So from here, we obtain the value of I output by using superposition theorem. Yeah, minus 1.5 milliampere, negative 1.5 milliampere, we obtain negative 3 milliampere. Okay. This one you haven't learned op-amp circuit, so maybe we can skip this. Yeah, maybe later. This is for the biomedical engineering student. Later, when after we learn op-amp, then we can discuss about this. This is inverter circuit and non-inverting circuit. So I will just skip this page. Now we go to another example here. Use source superposition to compute I output here at this resistor. So first, in the contribution due to the voltage source here, we calculate by open circuiting the independent current source here. So this is basically as a voltage divider, right? The current flowing through this I1 can be calculated by first calculating the equivalent resistor of the whole system. I1 equals to Vs divided by 6R here plus this one is 3R in parallel with 3R, because this is in series, this R is in series with this 2R. So this 3R in parallel with 3R. Okay. So from here we obtain IO due to the contribution of the independent voltage source equals to negative I1 divided by 2. Then short circuiting the voltage source, we calculate the contribution by the independent current source IS towards IO. So from here, this is yeah, it's better always to redraw if you are in doubt, because this one, what happened to this one? So basically this becomes a single node. Okay, so then we can calculate it like this. So the 6R is basically in parallel with the 3R here, and then in parallel with this 2R, and the I output is between this one, the current source and the branches of 2R and R. Yeah, this is the I output. It goes towards the R. So this is this branch. So this is the difficult part actually, how to redraw when you are short circuiting this, how to be able to make sense of the new circuit. Okay, so here this branch or this node, yeah, is denoted as 1, and similarly here we also denote as 1 to make us not confused, yeah, with the new circuit. And 2 here is this part, yeah? So this part, the upper node here. Okay, and 3 here will be somewhere here. Okay, this node. Okay, so from here we can use then the formula of current divider. The IO2, the contribution of the IO due to the contribution of the independent current source equals to IS here, yeah, divided multiplied by 2R here, divided by this one, 2R plus R plus the parallel resistor between 3R and 6R times IS. So we obtain IO2 equals to -2 divided by 5 times IS. So then IO can be calculated as IO1 plus IO2. IO equals to, and so this result plus this result, okay? And then we obtain IO equals to -Vs divided by 15R, yeah, this part, with -2/5 as IS, okay? So that will be all for the principle of superposition, current source superposition, yeah, either voltage source and or current source, independent current source or independent voltage source. Are there any questions from you?
Sir,
Yes.
how to withdraw the circuit in
How
the second?
to redraw?
Yeah, in the second one.
How to redraw the circuit? That's your question.
Yes.
Yeah. For example, this one, yeah.
Yes.
Yeah. The important thing is that you need to identify the nodes. Okay. Let's say here, yeah, for example, here, this is a single node, right? This is a single node. All this is a single node because they are connected. Yeah, single one. And the second, this is first node. Then we have this node. Yeah, connecting between the bottom part of the current source, yeah, and the one part of the resistor and the other part to the 2R resistor branch. Then we have another node. This one, yeah, this one is connecting the 6R resistor and the R resistor and the 3R resistor. So as long as the new drawing, you check the new drawing should be having these three nodes, then it will be correct. So for example, in this case, we draw first this current source to the leftmost part of the circuit, okay? And the upper part of the current source, which is here node 2, should be connected to 6R. So you draw here the 6R, the upper part, and then connected also here to the resistor 2R, which is here. And the other part connected to the 3R, drawn here. Okay, so let us try drawing it. For example, okay, so we draw the current source first, like this. Draw first this node number 2. Okay, connected here to the, you can, yeah, if you want, yeah, for example here the 6R, then the 2R for 1R first, yeah, 3R first, and then the other one is 2R. Okay, so we know that this one is the node number 2. Okay, node number 2. Then afterwards you check again. So this one, node number 3, connected at the other part, the other end, the other terminal of 6R here, with the terminal of the R as well as 3R. You know here 3R, so it should be connected. So this become node number 3. Okay, but then there is a resistor here R. Resistor R is connected to the other terminal of 2R. Here we have the terminal 2R, so should be here connected. So this become node number 3, and then here this become node number 1, which is connected to the bottom part of the current source, independent current source. So this is the node number 1. So then after that, you check again. So the important part is you should have the same number of nodes, in this case 3, and that node should connect the same branch as the original drawing. How's it, Nikki? So can you get it or still difficult?
So we can change the sequence of the resistance, yeah.
Yes, sure. You can change. For example,
Okay, sir.
you can change here after this one, something like this. For example, you draw first here 6R, right? And then you draw afterwards. It's better, of course, drawing here 3R, yeah, because 6R is connected with this. Yeah, you can draw also 2R. It doesn't matter, and then you can draw here 3R. Okay, so this becomes the node number 2. Your node number 2 here, according to this. Now the tricky part is the bottom part here. So this resistor R is connecting between 2R and 3R. So this one should be here, right? This R. But then this 3, yeah, this 6R is connecting to the 3R. Okay, the other part of 3R is 6R, through which cannot be, yeah, could be, it has to go through then. Oh, I'm getting confused myself. So this 2R, yeah. This 6R, the node 3. Now we find this becomes node 1, right? This become node 1. This become node 1. This should be connected with the bottom part of the current source. Okay, the bottom part of 6R. So this is not connected. Okay. This one should be connected then to where? To node 3. No, getting confused, huh? Confusing. But yeah, that's why it is making the correct sequence like this is important, such that what is important later, your node still, when you check again, this one should be the same as this one. So this one, the node 1, connects between the bottom part of current source here, with one part is with R, yeah, here, so it is connected really, so this is node 1, and the other part to the 2R. Okay, then the other end of 2R here is connected to the node 2. So this become node 2, which is connected also to the 3R, and the other part also the 6R. And node 3 is connecting between 3R, R, and 6R. Okay, 3R, R, and 6R. So 3R, R, and 6R. Yeah, so yeah, this should be connected through here, right? Somewhere. Yeah, I got confused when something like that. Any question again? Or Nikki, maybe you have still not understand. You haven't understood yet.
I think already understand.
Yeah, I think it's better to do exercises. Yeah, many exercises with given problem and practicing how to be able to redraw the circuit when you, for example, here this is done by short circuiting the VS here. If it is like this, the first part, yeah, which is obtained by open circuiting the IS, usually then the resulting circuit is simpler than the original circuit. But when it is short circuiting, then sometimes we get confused. Yeah. Okay, so if there is no more questions, then that will be all for today for the